Hi folks! The following video is our first one on substitution and elimination reactions. I'm going to be talking about a type of substitution known as SN2. Before getting into the specifics of substitution and elimination, I want to talk about alkyl halides. These are going to be our reactants for this chapter. The term alkyl halide refers to a molecule containing a carbon halide bond, and the alkyl part of this name refers specifically to a case where you have a carbon that is sp3 hybridized attached to your halogen. In reactions known as substitution reactions, you're going to have a nucleophile replace the halogen of your alkyl halide. The reactants of a substitution reaction would be an alkyl halide and a nucleophile, and your products would have a new carbon nucleophile bond, and you would have a halide anion formed. So in the substitution reaction, the nucleophile substitutes for the halide in bonding to carbon. Alkyl halides can also undergo what are known as elimination reactions. In this case, the alkyl halide is deprotonated by a base in a reaction that forms an alkene. Your starting materials would be an alkyl halide and a base, and in your products you'd have a new carbon-carbon pi bond, you'd have the conjugate acid of your base, and you'd have the halide anion. Today's video is going to talk about one particular type of substitution reaction mechanism. Within the alkyl halide, the halide plays two key roles. The first of which is that having this halide, which is fairly electronegative, is going to withdraw electron density away from carbon via induction. Due to the electronegativity difference between carbon and the halide, the carbon is partially positively charged, and the halide is partially negatively charged. The presence of this polar bond makes the carbon electrophilic, and recall that electrophiles tend to react with electron-rich molecules known as nucleophiles. So by depleting carbon of electron density, we're going to make it more reactive with electron-rich molecules. In substitution and elimination reactions, the halide also serves as your leaving group, meaning the component of your molecule, in this case an atom, that's separating from the rest of the molecule. Chloride, bromide, and iodide are good leaving groups because they are the conjugate bases of strong acids. And recall that strong acids form very weak and stable conjugate bases. Here are a few examples of good leaving groups. These are very stable conjugate bases, and they're able to separate from the compound as the leaving group because they're fairly stable by themselves. So some examples here are the halides iodide, bromide, and chloride. Notice fluoride is not listed among these. It is much less stable than the other halides. You also have sulfonates, where you have a sulfur-oxygen bond, where this negative charge is delocalized and spread by resonance onto the other two oxygens as well. Other good leaving groups are water and alcohols. Some examples of bad leaving groups are fluoride, which is fairly small and unstable, hydroxide and other alkoxides, where you have an O- attached to a hydrogen or a carbon, and also what are confusingly known as amides, which are different from those carbon-oxygen double bond with the nitrogen molecules. Amides can also refer to nitrogens with two bonds and a negative charge. Our bad leaving group examples are all conjugate bases of weak acids, meaning that these bases themselves are fairly unstable. To describe the structure of alkyl halides, I want to discuss some terminology. We'll label the carbons with Greek letters to describe their proximity to the halogen. The carbon that is directly connected to the halide is known as the alpha carbon, or alpha position. The carbons attached to the alpha position, one further away from the halide, are known as beta carbons, or the beta positions. And going one further away is known as the gamma position. Similar to the way we classified carbocations based on how many carbon substituents they had on them, we'll also classify alkyl halides based on how many alkyl groups, or carbon groups, are attached to the alpha carbon. We'll call an alkyl halide primary if the alpha position that's connected to the halogen has one other carbon group attached to it. If the alpha position has two carbon groups attached to it, we'll call it secondary. And if the alpha carbon of the alkyl halide is attached to three other carbons, we will call it tertiary. I mentioned earlier that substitution reactions involve a replacement of a halide by a nucleophile. I now want to talk about a particular mechanism of substitution reaction known as SN2. We're going to envision starting with a general nucleophile that is negatively charged, and here I've drawn a general alkyl halide. In the SN2 mechanism, I will have two curved arrows used at the same time. I use the lone pair from the nucleophile to form a bond to the electrophilic carbon that is alpha to the halide, and then I break the carbon-halide bond and bring those electrons to the halide. The first curved arrow is showing a nucleophilic attack. I'm bringing the electrons from the nucleophile to form a new bond to the electrophilic alpha carbon. And to avoid exceeding that carbon's octet, I have a loss of leaving group at the same time. My products would be a molecule with a new carbon nucleophile bond, and I've formed an anionic halide, X-. I would refer to this mechanism as a concerted reaction, because the nucleophilic attack and the loss of leaving group are occurring simultaneously. Concerted is a general term for when you have all of your bond breaking and bond forming occurring in the same step. Here's a more specific example of an SN2 reaction. I have an alkyl iodide and hydroxide. It's the carbon attached to iodine that is the alpha position, and because this alpha carbon has one other carbon attached to it, this is in particular a primary alkyl iodide. The hydroxide can serve as a nucleophile in my SN2 mechanism, which will have two curved arrows. I use one of the hydroxide's lone pairs to form a new bond to the alpha carbon, and I break the carbon-iodine bond and bring those electrons to iodine. The products here would be an alcohol with a new carbon-oxygen bond and the iodide anion. If we wanted to look at the rate law for an SN2 reaction, notice that the nucleophile and the alkyl halide are both involved in a single step. In terms of our rate law, this means that both of those concentrations will matter. Our rate will depend on a rate constant little k, the concentration of the alkyl halide, and the concentration of the nucleophile. We would refer to this as a bimolecular rate law, meaning there are two molecules involved in the transition state. The name SN2 comes from the fact that this is a substitution reaction where you're substituting the halide for a nucleophile. The N stands for the fact that it involves a nucleophilic attack, and the 2 in the name stands for the fact that this is a bimolecular rate law. With this mechanism in mind, I want to delve in a bit more and talk about a particular aspect of the stereochemistry for SN2 reactions. The term I'm going to use is stereospecificity, which simply means that the R-S configuration of the products depends on the R or S configuration of your starting materials. In an SN2 reaction, the nucleophile will always attack opposite to the leaving group. A consequence of how the nucleophile attacks is that SN2 will invert the configuration at the alpha carbon specifically. Let's consider a reaction of a sulfur anionic nucleophile and a chiral alkyl halide. In this particular alkyl halide, the alpha carbon is chiral. It has 4 different substituents, and if you assigned its configuration, it would have R stereochemistry. I'm going to draw the 2 curved arrows for this SN2 mechanism. I use a lone pair from the anionic sulfur to perform the nucleophilic attack at the alpha carbon, and I break the carbon-bromine bond and bring those electrons to bromine. Let's consider what's happening at the transition state. I have a simultaneous formation of a new carbon-sulfur bond, and I'm breaking the carbon-bromine bond at the same time. When I said that the nucleophile attacks opposite the leaving group, I mean that at the alpha carbon in the middle, you'll have the bromine directly opposite the incoming nucleophile. At the transition state, sulfur has a partial negative charge. The bromine that's leaving is developing a partial negative charge as well. And this alpha carbon in the middle is deprived of some bonds, so it would have a little bit of partial positive charge at the transition state. Notice that this transition state looks trigonal bipyramidal at carbon. Notice that the sulfur came in the way I drew it from the left-hand side. When I draw my product, I would have my new carbon-sulfur bond, where sulfur has added to the left, and if you looked at the stereochemistry here, this now has S stereochemistry. Notice going from my R starting material, I've had an inversion of stereochemistry to get to an S configuration instead. Without going through assigning R and S stereochemistry, there's a trick for drawing the product of SN2 reactions. You want to first check if your alpha position in particular is a chiral center. If it is, the inversion of stereochemistry will occur there. And what you can do is keep your carbon skeleton the same and just switch a wedge to a dash. Let's consider the following alkyl bromide and a general nucleophile. Identify your alpha position, and notice that in this case the alpha position is chiral. Imagine bringing in your nucleophile to the electrophilic alpha carbon and breaking your carbon-halogen bond. To draw the product quickly, because you had a chiral alpha position, you would want to switch the stereochemistry at the alpha position in your product. I could do that by, instead of drawing my nucleophile as a wedge, as the bromine was starting out, I can draw my bond to the nucleophile as a dash instead. Switching from a wedge to a dash indicates that there has been a change in stereochemistry due to this SN2 reaction. There are 3 trends that I want to discuss that relate to how the substrate or alkyl halide structure affects the rate at which SN2 will occur. The first of these trends has to do with steric bulk in the alkyl halide. SN2 substitution reactions will occur faster if the alkyl halide does not have much steric bulk. There's a trend we can see if we look at the alpha position itself. Methyl halides, where you have an alpha position with 3 hydrogens on them, are the most reactive towards SN2 reactions because hydrogens are small. As you add 1 carbon group to the alpha position, making it a primary alkyl halide, then going to 2 carbon groups attached for a secondary alkyl halide, and then going to 3 carbon groups attached for a tertiary alkyl halide, you're becoming less and less likely to undergo this SN2 reaction, and the reaction becomes slower. In fact, by the time you get to the point where you have 3 carbons on your alpha position, the molecule is completely unreactive toward SN2 reactions. The steric bulk at the beta position also matters. So let's consider we had an ethyl halide, where the beta position has 3 hydrogens on it. Then consider adding 1 carbon additionally to the beta position, versus 2 carbons attached to the beta compared to 3 carbons attached to the beta position. By the time you have 3 carbon groups attached to your beta carbon, your alkyl halide is not able to undergo an SN2 reaction anymore, just because it is simply too difficult for the nucleophile to squeeze in to kick out the leaving group. The second factor that we need to consider for SN2 reaction rates are the strength of the nucleophiles. I'll use the term nucleophilicity to describe the rate at which the nucleophile attacks an alkyl halide. And the stronger a nucleophile is, the faster the SN2 reaction will be. Some examples of strong nucleophiles that undergo fast SN2 reactions are halides, iodide, bromide, and chloride, negatively charged sulfur atoms attached to hydrogens or carbons, negatively charged oxygens in hydroxide or alkoxides, or cyanide, where you have an anionic carbon triply bonded to a nitrogen. Notice that all of these nucleophiles are negatively charged. Recall that the nucleophile needs to donate electron density to form a new bond to carbon. Molecules with an excess of electron density, such as in the form of a negative charge, will be better at doing this reaction, meaning they'll do it faster. In contrast, weak nucleophiles will undergo slow SN2 reactions, and weak nucleophiles will tend to be neutral molecules. Because they have less electron density compared to anionic molecules, neutral molecules like water or alcohols are going to be slower in reacting by an SN2 mechanism. The last trend I want to discuss has to do with the solvent that you're performing the SN2 reaction in. One thing to keep in mind, based on what I just discussed for nucleophile strength, is that SN2 reactions will usually involve anionic nucleophiles. So let's consider this general SN2 reaction with an anionic nucleophile. This is displacing a halide in the SN2 mechanism. Going from the starting materials to the transition state, the negative charge present at the nucleophile is going to be diminished. So before drawing the transition state, let's consider a general reaction coordinate diagram. For a concerted single-step reaction, I have a single energy barrier. And because I'm assuming that this reaction proceeds, I'm drawing the products as lower in energy than the starting materials to indicate that this is likely an exergonic and spontaneous reaction. If I looked at the transition state, I would have partial bonds between the alpha carbon and the departing halide, as well as a partial bond between the alpha carbon and the incoming nucleophile. I have partial negative charge on the nucleophile and partial negative charge on the halide. You could also draw partial positive on carbon, but it's not going to help us for the solvent effects, so I've omitted it here. The most important thing that I want you to notice is that from the starting material, where I had a full negative charge on the nucleophile, going to the transition state, I have diminished charge. A partial negative is less than a full formal charge of -1. So, going from the starting material to the transition state, you have diminished negative charge. And let's look at what types of solvents could stabilize the negative charges compared to those that will not stabilize them. The anionic nucleophile starting material is going to be stabilized if it can hydrogen bond to the solvent. We'll call those polar protic solvents. Some examples of these solvents are things like water, alcohols, carboxylic acids, or amines. These all have OH or NH bonds that could be donated to hydrogen bond or at least interact with an anionic nucleophile. These polar protic solvents will stabilize anionic molecules. And remember that the starting material is more anionic than the transition state. These solvents will selectively stabilize the anionic nucleophile starting material more than they will stabilize the transition state where you have just partial negative charge present. The negatively charged nucleophiles are going to be destabilized by what are known as polar aprotic solvents. These are solvents where you have electronegative atoms with lone pairs and polar molecules, but the solvent cannot participate in hydrogen bonding with an anion. Some common solvents you'll see are the ketone acetone, an amide solvent known as DMF, and a solvent where you have a sulfur-oxygen double bond known as DMSO. Think about your nucleophile, which has a lot of negative charge present, and then your solvent also has a lot of negative charge present at the oxygen end of it as well. The negatively charged end of your solvent molecule will repel the negative charge of the anionic nucleophile, which destabilizes the nucleophile starting material. The transition state, where you don't have as much negative charge present on your nucleophile as it's forming the bond to carbon, this will not be destabilized quite as much. So, if we consider the polar protic solvent, the ground state, the starting material, is relatively stable compared to the transition state. This means that there's a relatively large barrier with a large EA value. In the case of the polar aprotic solvent, think about your starting nucleophile as being higher in energy, because it can't participate in any hydrogen bonding to stabilize it. It's higher in energy, which actually makes getting to the barrier require less energy, corresponding to a lower EA value. The barrier for SN2 in the polar protic solvent is larger than the barrier in the polar aprotic solvent, so we would say that SN2 is faster in polar aprotic solvents, ones that cannot donate hydrogen bonds to stabilize the nucleophile. In summary, today's video introduced the ideas of substitution and elimination reactions, and I've talked in depth about the SN2 reaction. This is a particular mechanism of substitution reactions. I discussed the rate law, I discussed the transition state and stereochemistry, and I discussed some factors that can affect the rate of SN2 reactions. That's it for this video. I will see you in class.